All right, Sheen just pointed out that you can't do one of these problems, these functional groups, with just 4 carbons because the benzene ring itself has 6. So we're going to act like it's just 4 carbons and throw a benzene ring on it. Okay, so we've got, you could do something like there's a double bond, there's an alkene, there's an alkyne, it's got a triple bond on it. There's an alcohol group. There's a aldehyde. There's a carboxylic acid. There's an amine. There's an amide. Oops, that's too far. There's ether.
Is that O just supposed to be in between 2 carbons?
Yep.
On,
Yep. That's an ester. Alkyl halide. Cycloalkane. Heterocyclic ring structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then the 13th one would be, I'll just put 4 carbons. And then a benzene ring here. Anybody have any questions about those?
The squares,
Sure.
can you just explain them, please?
They're just carbons connected up to each other. So it's just carbon, 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 carbon. So it's a ring structure, right? And then each one of these carbons needs 4 bonds. So what's not being shown are the 2 hydrogens on each. And the only difference between this one and the other one is the corner down here has a nitrogen in it, and nitrogens only have 3 bonds, so that's why there's only 1 H there. So we would erase out that. A sec, sorry. And then we could put in an N with an H on it, and that would be that one. Is that good?
Yeah.
Okay. We want to name these 5 molecules. Okay, great. So the longest continuous structure for this first one is 1, 2, 3, 4, 5, 6. All right, so there's number 1. And so on number 3 and number 4, they are both methyl groups. So I have a 3, 4 dash dimethyl. What do we say it was? 6?
And how do you know that they're methyl groups?
I don't understand the question.
Like, how do you look at this and then tell that it's a methyl group? I forget.
What
It's one.
Oh, single bonds.
what are these things I'm circling?
Carbons.
Okay, so each one of those is a carbon. So the ones on the ends are carbon groups, and since they're only bonded to an adjacent carbon and then it's not showing anything else, then it has to be 3 hydrogens.
Okay.
So this one here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, okay, it doesn't really matter. All right, so I'll just go straight across here. So here's number 1. And so on number 3, I have a methyl group and I have an ethyl group. So I'll say 3 ethyl, 3, methyl, pentane. We good?
And it's ethyl then methyl because that's alphabetical, right?
Yeah, yeah. Okay, so what we have here is a cycloalkane. consisting of 3 carbons, and we've got these 2 chlorine groups on here. So we could say so cyclopropane takes care of these atoms. So what's attached to my cyclopropane?
Chlorine or
Chlorine.
So I have 2 chlorines, and we call that a chloro, and 2 of them is a dichloral, and they're on positions number 1 and 2. Because it's a circle, I can make either one of them number 1, so it doesn't really matter which one's 1. And then I go the closest route to get to number 2. Same kind of situation with the next one. It's 1, 2, diiodo, cyclohentane. And then the last one here is 6 carbons and then a methyl group. Okay, so we have a methyl, hexane.
ANE refers to the bonds, right?
And the what?
The ANE, the ANE refers to just single bonds, right?
That is correct. It's an alkane. All right, so we want to draw stuff here. So I've got 2 carbons, okay? And then I've got 2 chlorines, and one of them's on carbon number 1, and one of them's on carbon number 2. So you could draw it like that, but since it's only 2 carbons, maybe you draw it like this. Something like that. Doesn't matter where the chlorines go as long as one of them's on number 1 and one of them's on number 2. Hexane, 2, 3, 4, 5, 6. And on carbon number 2 there's a methyl group, and on carbon number 3 there's a methyl group. So that's that one. Propane, 2, 3. And then on number 2 there's a methyl group. Butane, 2, 3, 4. And then on carbon number 2 there's a bromine. That's it. We good with that?
Yes.
All right, so we're identifying functional groups. So this one has an alcohol. This one has an alcohol and an alkyl halide.
I thought the fluoro just meant like fluorine is in the structure.
True. But fluorine being in the structure. Hey, shut up. Fluorine being in the structure is an alkyl halide. Halides being the second to last column on the periodic table. So here's an alcohol and here's a fluorine. So this is an alkyl halide and an alcohol. Over here, I just have an alcohol. Here, this is an aldehyde. Here, this is 2 aldehydes. That aldehyde. This aldehyde. So I just want to make sure we understand. This line right here is just going to a hydrogen. Same thing with this one and this one and this one and this one. This one here is a line going to a carbon. And you know the difference because this one here has C's drawn. So if it was just a line, then if it was another carbon, if there was another carbon right there, then the C would have been drawn. But since there wasn't one, then the thing that is missing is a hydrogen. So this right there is a ketone. That is another ketone. This one's super easy. It's an amine. It actually just says it straight away. This one has side chains, just an amine and an alkyl halide. Cannot spell. This one here, this is an amine. This and this is two amines. An amine on the butanamine, an amine, or sorry, I just messed both those up. Those are both amides, obviously, because it says amide there. This one, amide. This one, amide. This one is a carboxylic acid. This one is a double carboxylic acid and an alkyl halide because of the chloro. This acid, carboxylic acid. This is a carboxylic acid and an alcohol. This ester. And this one, ester. Oh, looks like I skipped some. Butanoate, ester, ester. Okay. Do we have any questions about those guys? All right. Let's hop back over to the notes. And so let's do the first naming of the functional groups. And we'll start off with the alkenes. So it's a double bond. When we start naming things that have functional groups on it, whatever is the most reactive thing, that's going to be my primary focus of the name of the molecule. Because there might be something else that's reactive on it, but the most reactive thing is the most important part of the molecule. And that's what the name is going to be composed of. So for the alkenes, we're talking about something that's got double bonds on it. We're going to use all the same nomenclature, except we're going to end this as in an ENE, which means we've got a double bond. So this one here has a double bond in it. It's got 1, 2, 3, 4 carbons. And the double bond starts at carbon number 1 and it spans to carbon number 2. So this is butene and it's 1 butene. This is 2 butene because it starts at 2 and goes to number 3. I'll come back to the cis in a sec. And then this is 3-fluoryl 1 butene. So what's more reactive, the double bond or the fluorine?
Fluorine.
Does it look like that with the name for this molecule?
You said reactivity, or the most reactive comes first, right?
No, I didn't say that. I said the name of the molecule is dependent upon the most reactive thing. But that doesn't mean it's written first. If fluorine was more reactive, then the fluorine would be designated as side chain number 2 instead of side chain position number 3. So what we're saying is the most important part of this molecule is this double bond. So because of that, this double bond is closest to this end here. So that gets to be number 1. If this fluorine had been more reactive, we would have said that this was number 1 because then it's closer to this end. But since it's not as reactive as the double bond, this gets to be carbon number 1. So then I say my double bond goes from carbon number 1 to carbon number 2, and then on carbon number 3, I got this fluorine here. So 3-fluoro-1-butene. And then the next one, it's double bonds. So this die is 2 of these things, and the double bonds, so here's carbon number 1 and number 2. So from 2 to 3 is a double bond, and then from 3 to 4 is a double bond. So that's why it says 2,3 hexene diene. We good with that? So 2, 3, 4, 5, 6, 7, 8. Can you name that for me?
Um, 4 comma 1, 2, 3, 4, 5, 6, 7, 8. Would it be like oct because there's 8 carbons?
Yep.
Oct, octane. Do you?
Because there's a double bond.
Oh,
Why does the butene down there have cis then?
We're going to talk about it in a bit. So the triple bonds are, let's back up 1 second. What's different about this carbon, say, right here? How many hydrogens are there?
none.
One.
One. Normally in a carbon chain, there's 2 hydrogens there because it's connected to 2 carbons. That leaves 2 of the 4 bonds not accounted for, so you put 2 hydrogens on there. But since there's a double bond there, that means it's bonded to 1 carbon twice and another carbon once, so that's 3 bonds. So there's only 1 bond left, and so there's only 1 hydrogen there. So the triple bond stuff is basically exactly the same as the double bond stuff, except it's a triple bond. And so I say "-ine" instead of "-ene". So the positioning is the same. So this is 1-butene, 2-butene, 3-fluoro, 1-but. Sorry, I should be saying "-ine". Y-N-E is "-ine". So 1-butyne, 2-butyne, 3-fluoro, 1-butyne, and then 1,4-hexadiene. Can anybody tell me, like I copied the molecules from right above, right? Here to there, here to there, here to there, here to there. Why didn't I exactly copy the last one? It's close, but it's definitely not the same thing.
Because it's not possible to have 6 bonds on a molecule.
Right, that's exactly it. If I put my triple bond right here, not that it's not possible to have 6 bonds in a molecule, but this poor carbon right here would have 6 bonds on it, and that's not possible. It can only have the 4. But there's really no difference between the enes and the ines, except that I'm looking at a double bond instead of, or a triple bond instead of a double bond. And I changed that suffix to YNE from ENE. What do you know about double bonds?
They're stronger than single bonds, but weaker than triple bonds.
Anything else?
Reactive.
They're very, very reactive. Do you remember why?
Because the electrons are accessible because they're in pi bonds, right?
Yep. So the single bond has the 2 electrons sandwiched between the carbons. And then because I'm doing a double bond, the electrons are above and below. And so these electrons right here are exposed. So double bonds are super reactive. So when we were talking about something like ozone, the UV light that gets blocked by the double bond. Okay, let's do a little bit of aromatic nomenclature. So any molecule that has a benzene ring on it is considered aromatic. And we talked about benzene rings before, where the benzene rings themselves were super dangerous because they were sort of like I don't know, Chinese throwing stars because there isn't anything attached to them and they're very flat and so they can cut through stuff. But the moment you attach something to the benzene ring, it becomes not reactive, not dangerous. So, like both vanilla and cinnamon are benzene rings with stuff attached to them. So the moment you've attached stuff to the benzene ring, the chemical reactivity completely changes. So there's two ways you can name the aromatic, and benzene rings will be referred to as aromatic because most of them have a scent. So obviously you know what cinnamon smells like, and you know
Oh,
um, what vanilla smells like. So a lot of the things that you smell have a benzene ring on them.
Professor Kovacic.
Yeah.
Why are they drawn like that with like the circle in the middle?
Because that's what the electrons are doing.
They're circling on the inside.
Well, they're circling above and below the 6 carbons because it's a delocalized system where it's not double bonds alternating. It's actually like a bond and a half length. This is like 122 stuff where the double bond that are between 2 carbons actually keeps jumping on each
Yeah.
carbon. And so you end up with a donut shape of pies on the top and a donut shaped pies on the bottom. And you end up with a circle of where the electrons are found. So that's just a way to draw it. It can be drawn like that, or it can be drawn like this down here.
Okay.
Either one is fine. But this one with the circles in it makes more sense.
Yeah.
So there's two ways you can name an aromatic hydrocarbon. You can either name the molecule for the aromatic hydrocarbon, or you can name it as a side chain. So in this first one up here, it makes more sense to name it as a side chain because the longest, otherwise you're going to name a side chain on a chain. So this first molecule has this benzene ring side chain and has this methyl group side chain. So it makes a lot more sense for me to say, okay, I got this molecule with these things I have circled attached to it. Over here, I've got this thing, but there isn't anything else on it. So what I could say is that's my main chain, and then there's 4 carbons attached to it. So either of those methods are perfectly acceptable. So this one is 2-methyl. So this is carbon number 1 and carbon number 2. So there's my 2-methyl, and then 5-phenyl. 5-phenyl. So carbon number 3, 4, and then carbon number 5. Over here, though, I say benzene because this is a benzene, and then this is a butyl group attached to it. But remember, this is attached to carbon number 2 on my 4-carbon chain, so this guy gets called sec-butyl. Okay, so there are lots of molecules that the base structure is a benzene ring, and then I can add stuff to it, 1 or 2 things. And there's many, many molecules that have 2 things attached.
Why
And
not more than 2 things?
they start to crowd each other out. I'm not saying that it can't happen, but it makes the reactivity of them pretty substantial. So do we know what this molecule is?
TNT.
So what do you know about it?
It's very reactive.
It's very reactive. So a lot of this has to do with the fact that there are 4 things attached to a 6th ring structure. So these things aren't very far from each other. So they literally trying to push each other off the ring structure. But two things on the benzene ring structure is more compatible with the electron forces, since there's only 2 things instead of, in this case, 4 things. So there's several ways we can name these. So we'll just use this first example. If the carbons are right next to each other on the ring chain, then you can refer to that as ortho, or O, or 1,2. If they're a carbon away from each other, then you can refer to that as meta, or 1,3, or just M. And then the last one, they're on opposite sides of each other, so that's going to be referred to as para, or 1,4, or just P. Is that okay? So there's literally many, many different ways you can name these molecules. The one with the numbers is actually the official name, but the ortho, meta, para stuff gets used an awful lot. You'll see para and meta and ortho written on like a shampoo bottle or a bottle of conditioner listing the ingredients. In the same way, nobody says dihydrogen monoxide. So we also have these 6 benzene rings with functional groups on them. So do you know what toluene, where you experience toluene? It's what the main ingredient for modeling glue. So if somebody is sniffing glue to get high, they're actually displacing oxygen out of their brain by smelling toluene. So their brain fills up with some toluene. Not a super smart thing to do. So what toluene is a benzene ring with just a methyl group on it. If instead of a methyl group, I put an OH on it, then I've got something called phenol. So the benzene rings can also be called phenols. And so an OL is an alcohol, so they just mash them together and say phenol. How about the third one? Do you recognize that word?
Styrene? Like,
Polystyrene.
So if you have polystyrene, you have this molecule over and over and over again, and you end up with styrofoam. There are different densities of styrofoam based on how fast you allow it to be created. Some of them are super soft, and some styrofoams are actually really, really structurally sound, right? They'll build like sink basins and lots of different things you can use structural styrofoam for. What's like you might be a person who's like, I'm never using styrofoam because it's bad for the environment, but you're still using it. Does anybody know where you're definitely using it, even though you probably don't know you're using it there?
Isn't styrofoam in your car
Where?
bumper?
It's your bumper. The bumper used to be made out of metal, but that's not really a good object to use as a, I mean, what's the bumper's job?
to keep your car from getting damaged?
Okay, but I don't care about my car. I care about me getting damaged. So,
Yeah.
to absorb the impact into the bumper and not into you.
yeah, so initially you were correct, Annika, that the bumper was to protect the car. And then so many people were dying that sometime in the late 70s, early 80s, they changed the bumper. And so now they think about the bumper not as some sort of ramming device, but as a way to absorb energy. And it has a completely different name now. Does anybody know what they call the corners and the fronts and backs of cars?
Like crush zones or something like that?
Yeah, it's close. It's called a crumple zone. So if I'm going to crumple something, it takes effort to crumple it. So what happens is the car, this is why new cars get totaled at a much higher rate than old cars, because they purposefully crumble. That way, that crunching that happens absorbs energy. Instead of that energy being transferred to you, it's being used to crunch up plastic and styrofoam in your bumper. So it might be a minor hit, but your bumper's hosed because your bumper's made out of styrofoam. The next one looks like there's a formatting here, but that's a carboxylic acid attached to the benzene ring, and so it's benzoic acid. And if I put an aldehyde on there instead, then it's benzaldehyde. And then if I put an amine group on it, it's aniline. And so then I can make different names for these things. So if I put, I don't know, let's say just I put a chlorine here. What's the relationship between the methyl group and the chlorine on the toluene? Their position is one away from each other, right? So
They're
then,
ortho?
so then they're ortho to each other. So I could say, I'm going to write this. I'll put it over here. Ortho, what? We good with that? So from this name, remember the only reason to have a name is so you can draw a molecule. So from this name, I see this and I say, okay, I got to draw a toluene. All right, great. Boop, 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 boop. There's a toluene. Oh, and there's a chlorine on it. Where is it on the ring? It's ortho to the toluene's methyl group. There you go.
So then just do the like 1, 2 instead.
That 1, 2 would be totally fine. But if you're given this name, you're still going to have to be able to draw that.
So we've got ortho,
Meta and para.
para. What does meta like? What does meta mean? Because I know para is like parallel.
Para is opposites, and meta is middle.
I think it's like I think like parapsychology or something, like metaphysics.
Yeah. I don't know if I'm gonna go there, but okay. So let's talk about naming alcohols. So same situation that we had with the benzenes, sorry, with the alkenes and alkynes. I want to give the position of where the alcohol group is. So I'm going to change the suffix from A and E to an OL. So I've dropped the E off, and then instead of having it be ethane, it's ethanol. And then I put the OL on there. So how come there isn't a 1 here?
Because it's too obvious.
That's fine. I mean, it couldn't be anything else, right? If there's a single alcohol group and it's 2 carbons, where is it going to be? It's going to be on one of them. So whichever one it is, it's number 1. So I don't need it. This one here, on the other hand, though, I'm going to need to put down 2-propanol. How come?
Because it could be somewhere else.
Where else could it be?
Could it be on any carbon?
Okay. So what would the name be if I took it off of here and I put it right here?
1-propanol.
That'd be 1-propanol. And then what if I put it over here?
Wouldn't it still be 1-propanol?
It'd still be 1-propanol. What if I put it right here?
That would still be 1-propanol.
Still be 1-propanol. So my only options for this, it's either on carbon number 1 or it's on carbon number 2. This one is saying I've got an alcohol, I'm sure of that. I've got 2 of them. My ring is 5 carbon, or sorry, my chain is 5 carbons long, and my position is carbons number 2 and number 4 for my alcohol groups. So 1, 2, 3, 4, 5, and we've got diols. And then the last one, I don't need a number for it because it's a circle. So it doesn't matter which carbon I put it on. That alcohol group is going to be on carbon number 1 on my cyclopentane. We good with that? Okay. All right, so there's a couple of different nomenclatures for the ether. One is...
What are the properties of ethers again? Because I remember we worked with them.
They're volatile. They displace oxygen in mammalian respiration systems. And it's obviously the only thing that ever makes Wonder Woman incapacitated. I don't know why, but every time she gets incapacitated, somebody puts a cloth over her mouth with an ether on it, which never made sense to me since she's like the Flash fast. Like you'd think she'd see it coming and just like, I don't know, move out of the way or blow. Or hold her breath and then give the guy an elbow that breaks all the bones in his body. That seems like a good idea, but whatever. So in this case here, we've got an oxygen sandwich between carbons, and all the carbons have to be just alkane carbons. No double bonds, no triple bonds, no carbonyl carbons, no carbons doubly bonded to any oxygens. So what we do here is, for the IUPAC nomenclature, we use the same kind of thing where we say, what's the longest carbon chain? So there are only 3 carbons here, 1, 2, 3. So the longest carbon chain is 2. So I'm going to say that this thing, oh, it looks like, sorry, I'm going to go to the IUPAC ones down here. 1, 2, 3. So the longest carbon chain is 2. So I just say, all right, so I have an ethane here. And then what's attached to my ethane? There's a single carbon right here, so that's meth. And then oxy. So what we're saying is I got this ethane with an oxygen attached to it, and on the other side I've got a methyl group. So for this one here, we're saying I've got a butane. It's 4 carbons long. So 1, 2, 3, 4. And attached to it, there's an oxygen. And then on the other side of the oxygen, there are 2 carbons. And all of this is attached to position number 1 on the butane. So here's position number 1. And then I have my oxygen, and then I've got 2 more carbons, so that's why it's F. And then the last one here, it's propane, 1, 2, 3. And attached to my propane, there's an oxygen at position number 1. And then on the other side of that, I've got this benzene ring. So 1-phenoxypropane. The non-IUPAC nomenclature for this is you recognize that you have an ether. All right, great. I got an ether. So boop, 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 ether. So what's right here and what's right here? So over here, I've got a methyl group, and over here, I've got an ethyl group, and they're connected to each other by an oxygen. So I say methyl, ethyl, ether. And the next one is going to be butyl ethyl ether. Why? Because on one side of my oxygen, I've got 2 carbons, and on the other side of my oxygen, I've got 4 carbons. And then the last one is phenyl propyl ether. Why? Because on one side of my oxygen, I've got a phenyl group, and on the other side of my oxygen, I've got 3 carbons. So you can use either nomenclature to describe those. You probably see some of these names if you go to like a hardware store looking for maybe paint thinner or some other kind of solvent. So thiols are just like alcohols, except I substitute the O out for an S, and the THI is an old nomenclature for sulfur. So if you have something like 1-butane thiol, what I immediately think of is this smells. So all of these SH groups, all of these sulfurs, they're all going to be smelly compounds. And what produces these smelly compounds, usually? Yeah, things that are decomposing. So usually it's going to be a bacteria is going to be decomposing something and producing thiol gases. So in this case, I've got 1-butane thiol. Why is it 1-butane thiol? Well, it's 4 carbons long, so that's why it's butane. And then the thiol group, the group that's an SH, is on carbon number 1. So that's why it's a 1. And then the next one is also a butane, so it's 4 carbons long. And it's got a thiol group on it, and it also has a methyl group side chain. So I've got thiol at position number 1, methyl group at position number 3. And then my last one here, it's again a butane, 1, 2, 3, 4, except looks like I went the other way with that. 1, 2, 3, 4. And so then I've got a thiol group on number 1 and a thiol group on number 3, and so it's 1,3-butane dithiol, telling me there's 2 thiols on positions number 1 and 3. Are we good with that? The next one's an aldehyde. So aldehydes are easy to locate or easy to identify because they have to be on the end. Why do they have to be on the end of a carbon chain?
Because they can't have as many bonds. They can't have multiple bonds, or
No.
they.
So I've got this carbonyl group thing, the C double bond O, and on one side I have to have an H. That's a requirement for an aldehyde. I could have 2, 1 on each side, but then that's just 1 molecule because hydrogens can only make 1 bond, so that's formaldehyde. So this is 1 H on the one side, and then there's a methyl group on the other side. So this is 2 total carbons long, so it's an F, and then the Al is letting me know that I have this structure here. So the reason you should be able to identify these quickly as aldehydes is because they're always terminal. They're always at the end of a molecule. You can't have an aldehyde in the middle of a molecule. It always has to be at the end of a line structure because it has to end in an H. And there can't be anything on the other side of the H because the hydrogen can only make the 1 bond. So you should be able to quickly identify the aldehydes because of their positioning. So does the next name make sense? It's 1 carbon longer, so it's propane and then Al. So when you say these, you say al, like Albert kind of thing, because we don't want to get them confused with any of the other suffixes. And then the next one is just one longer. Like the aldehydes are pretty boring. I can't really do anything except make a structure and then attach a C double bond OH to the end of it. And then that's it. That's an aldehyde. Do you guys know what molecules are aldehydes inside your bodies?
What do we have formaldehyde inside of us at any time?
No. Not until you're dead and somebody's embalming you, which hopefully doesn't happen. The embalming part.
Yeah, that's pretty bad.
Glucose is actually an aldehyde.
Huh.
Okay. Some common names for aldehydes. So all we do is we say the name aldehyde, and then we identify how many carbons are there. So the first one is ethyl aldehyde. Why? Well, it's obviously an aldehyde because there's a C double bond O there with an H on one side, and it's only 2 carbons long. So I just say ethyl aldehyde, propyl aldehyde, butyl aldehyde, octyl aldehyde. So they're super easy. Then there's some super common names: formaldehyde, and then acetaldehyde, and then benzaldehyde. We already talked about the benzaldehyde one. Acetaldehyde because ACE used to mean 2 carbons before they went to F, in the same reason that acetic acid is 2 carbons, or an acetate is 2 carbons, just old nomenclature. You could see a bottle of this, or it could be an ingredient in something. Do we know about formaldehyde? How we thought it was fine, and then we've come to find out that it's a carcinogen and a respiratory irritant?
Oh no.
Were people drinking it or something?
No, they were being exposed to it from glues that when they get wet and warm, the formaldehyde comes out.
Oh, lovely.
So people were doing things like plywood as portions of their bed frame, and then over time, the plywood will degas the formaldehyde because of the heat and moisture in the house, and then these people would have respiratory ailments or weird cancers, and so it's a plywood issue because the plywood itself is stuck together with a glue that has formaldehyde in it in the same way that the IKEA stuff does. So if you get IKEA furniture wet, you should throw it away, which probably isn't difficult for you to do because as soon as you get IKEA furniture wet, it starts to disintegrate, right?
Yeah, and it sucks anyways.
I mean, if you could even put it together in the first place.
Okay, Deadpool.
I've had an IKEA bed, and like I accidentally leaned back on it too hard, and the entire back frame just kind of detached from the freaking the floor parts, and it was really annoying.
Yeah.
But it makes you feel like a true Swedishman. I mean,
All
if I sleep in an IKEA bed and I want Swedish meatballs the next day.
You just go to Portland then because they've got them there.
I make
Okay,
my own.
so ketones. Ketones are similar to the aldehydes with the exception of they cannot be at the end. There has to be a carbon on the other side of the carbonyl group. That's their definition. So the smallest ketone is a propanone because I have to have a C double bond O and then I have to have C's on both sides. So I have to have a minimum of 3 carbons. So there aren't any 2 carbon aldehyde or ketones because I need a minimum of 3. So these aldehydes can be in the middle of long carbon chains or in the middle of ring structures. You can't have an aldehyde on a ring structure because the carbons are all attached to each other. So here's a propanone, and then there's butanone, and then there's 3-pentanone. Why do the first 2 not have numbers and the third one has a number?
Well, in the first one, there can only be one location.
Correct. They can only be on that middle carbon.
I don't know about the second one though, because there are 4 carbons.
Okay. So you know that the ones on the end can't have the C double bond O on them because they have to be on the ends. But if I put it, if I leave it where it is, or if I put it right here, it's the same thing, right? It's still one
Yeah,
away
it
from
would be
the
the
end.
same thing anyway.
So it's the same way. It doesn't matter anything. This one, on the other hand, though, it could be at position number 3, or I could move this C double bond O to position number 2. So I'm going to have to designate where the aldehyde actually is located. And I don't on the cyclohexanone because it's a circle. So whichever, doesn't matter where it is, that's still just going to be carbon number 1. So I just don't even bother to put one down. Common names for this, they're very similar to the ether names. So I'm looking at this molecule and I identify this. All right, that's a ketone because there's a C double bond O and then there's a carbon on each side. So what are they? There's a methyl and a methyl. So this is dimethyl ketone. This is definitely sold in almost all hardware stores. This one is methyl ethyl ketone. Why? Because there's a methyl group here and then there's an ethyl group here and this forms a ketone. And then I've got methyl phenyl ketone. So methyl phenyl ketone. I didn't have a common name for the cyclohexanone. And then there's some very common names. Acetone. Again, this is the 2 carbon thing. So we're saying I've got a ketone and then I've only got 2 more carbons. And so that's why it's acetone. And then this guy here, this methyl ethyl ketone, that's where the MEK comes from. So you'll see MEK written on paint on solvents at the hardware store, and that's where that comes from. Carboxylic acids have something in common with the aldehydes. What is it?
The double bond O.
Okay, but that's the same for the acetones, and the carboxylic acids don't have this thing in common with them. So what's the aldehyde connection?
Has to be at the end.
Has to be at the end because this ends in an H, just like the aldehyde ended in an H. Instead of it ending in just a CH, it ends in a COH. But regardless, it ends in an H. So this thing has to be named or has to be terminal. So you'll be able to find these pretty easily. They'll be at the end. So if it ends in a C double bond O OH, it's an acid. If it ends in a C double bond H, then it's an aldehyde. Oh, let's back up one second. Do you guys know where the ketones are in your body?
Aren't they like fat?
Could be, but this is fructose. So glucose is an aldehyde and ketone is fructose. So when you eat table sugar, you've got an aldehyde and a ketone there. Okay, so for this one here, I knocked the E off the end of it, and then I put OIC for oic and then acid. So this is ethanoic acid because it's 2 carbons. So I dropped the E off the ethane and put oic acid. And then I've got propanoic acid. And then the next one I've got propane dioic acid. So my only options are I could put the acids at the ends and that's it. We put up, pretty sure we had, oh, we definitely did. We had the citric acid molecule on a homework question. And so do we see all of the acids? C double bond O OH, C double bond O OH, C double bond O OH. So there's 3 acids. So we said that citric acid was polyprotic. Maybe that one's a better one. Okay. And then we've got esters. So the thing that you need to understand about the esters is how it's made. So the way you create an ester is by taking an alcohol and reacting it with a carboxylic acid. And so when that happens, a water molecule is made, and then the 2 substances get linked together. So let's, I don't know, let me do, if I just grab this. This right here. Now get the whole thing. Copy. Okay, so I wish I could see that side. Okay, so how is this molecule made? Well, it's created when an alcohol and a carboxylic acid come and connect to each other. So what do you have? What constitutes a carboxylic acid? What do you have to have? I'm gonna fall asleep.
Hey, you have to have a hydroxide and then, or not a hydroxide, but an OH and a double bond O.
Gotta have that, right? So this red portion of the molecule up here, that's the carboxylic acid that I started with. So I started with this carboxylic acid, and what did I react it with?
Alcohol,
Okay, so I've got an OH. Great. What's attached to it?
carbons,
Just a CH3. How do I know it's just a CH3? Because there's only a CH3 here. So when this reacts, I take the acidic H off of the acid and I react it with the alcohol group on the alcohol and I make myself a water molecule. Okay? So now, darn it. That bond on that oxygen and that bond on that carbon are missing. So the oxygen only has one bond, it needs two, and that carbon on the right only has three bonds and it needs four. So what do these two substances do? They connect to each other. And then we get that. This is how we make aspirin. This is how you made aspirin.
oh yeah,
You had methyl salicylate and acetic anhydride. So alcohol group, acid, put them together, aspirin. And so then the other thing that's supposed to be here is that guy would go right there. So tell me about the acid. Okay, so let's back up a sec. The reason this is called methyl ethanoate is because the acid that it came from was methanoic acid, and the alcohol it came from was methanol. That's how we get the name from its two reactants. So what were my reactants for this one here, for this next one? Where do I break this molecule? What was here was an H, and what was here was an OH, and that went and made myself a water molecule. And now I need to connect them up because the oxygen is missing a bond and the carbon is now missing a bond. And so that's where the connection came from. So this used to be an alcohol. So I'm going to say ethyl. And this used to be propanoic acid. So I go propanoate because that's what we did when we went from an acid to a polyatomic ion. And then we end up with ethyl propanoate.
So we started with propanoic acid and ethanol.
Yes. So what did we start with for this last one? What was the acid that I started with?
methyl acetate.
What?
I said on methyl acetate. Like which one are we talking about?
The one we haven't talked about yet.
Mm, acetic acid.
Acetic acid. So the red section is the remainder of the acid that I had, and with the acid, the H is the reactive part. So the H came off, and that left. So I've got acetic acid because it's 2 carbons, and then what was the alcohol?
Ethanol or methanol?
No, definitely not.
Uh,
The black portion of that molecule is what?
Benzene.
It's a benzene ring. What did we call a benzene ring with an alcohol on it?
Oh,
A phenol. So this was a phenol and ethanoic acid. So the phenol becomes phenol, and the ethanoic acid becomes ethanoate. And so then I end up with phenyl ethanoate. These, do you know anything about esters? They're flavorful and aromatic. Not in the chemical sense of aromatic, but they've got they smell usually good. Okay. So then we'll talk about amines now, and there's a couple of ways to do the amines. There's a chemical abstract, which is a particular nomenclature form, and then there's the IUPAC name. So something else we need to recognize is the amines can be attached with 1 carbon or 2 carbons or 3 carbons. And so that makes them a primary, secondary, or tertiary amine, and that changes the reactivity greatly. So this first one here is 1 carbon attached to a nitrogen. So then I'm going to call that methane amine. Why? Well, a nitrogen attached to a carbon, that's an amine. Okay, so great, I say an amine. And then how many carbons are there? 1. So that's why it's methane amine. So this next one is, here's my amine. So I picked the longest carbon chain that the nitrogen is attached to. So that's ethane amine. So these 2 carbons are the ethane, and the carbon-nitrogen connection is the amine. But now this nitrogen also has something else attached to it, and it's a methyl group. So how do I designate that? I say N-methyl. So what this is saying is I've got on my nitrogen, I also have this methyl side chain, plus the nitrogen is attached to 2 carbons. And so there's my ethane amine. And then my last one down here is still an ethane amine, so I'm just going to change out this hydrogen for another methyl group. So I've got ethane amine because it's a nitrogen attached to a carbon, and the longest chain is 2 carbons long. So there's my ethane, and then there's my amine. Well, what else is attached to the nitrogen? 2 methyl groups. So I say NN dimethyl ethane amine. The other nomenclature is the IUPAC nomenclature. I don't know. It depends on my mood as to which one I'm going to use. But basically what the IUPAC does is treat the amine as a side chain instead of a functional group. And so I've got a methane group here. What's attached to it? An amino. So this is amino methane because it's a nitrogen attached to a 1 carbon molecule. So this is a 2 carbon molecule, so I'm going to just call this ethane, and what's attached to my 2 carbon molecule? An amino group, meaning a nitrogen with H's on it. This one is 2-aminobutane because I've got 1, 2, 3, 4 carbons, and on carbon number 2, there's an amine group. So 2-aminobutane. And then the last one, I've got aminoethane plus I've got on my methyl group or on my nitrogen, I have a methyl group attached to it. So I have to designate the fact that the nitrogen has an extra methyl group on it plus it's attached to this ethane group. These molecules are important because they usually constitute something that would increase heart rate, increase blood pressure, and increase respiration. So what does that? What bad thing does that in the community?
Meth.
Meth. Yeah. So tell me about the meth then. What is the meth molecule must have on it?
Well, carbons for sure, and
Specifically one carbon, right? Because it's meth.
yeah.
And then what else must it have on it after what we just talked about?
Hydrogens, and then a methyl group, or
Yep, there's a nitrogen attached to a methyl group somewhere in the molecule. I mean, it's not giving you the full structure at all because they're just saying the word meth. But since we know it's an amine and it's going to have a nitrogen with a meth side chain attached to it. So this thing right here, that's the main proponent of methamphetamines. Okay, so the amines and the amides look very similar because they both have nitrogens on it, but the interesting quality of the amides is when the nitrogen is attached to a carbon, but that carbon is this carbonyl group carbon, these things become depressants. I don't mean like something that causes depression, but I mean something that slows heart rate, lowers blood pressure, slows respiratory rate. And these are kind of like the esters, where I'm going to start with carboxylic acid, but instead of an alcohol this time, I'm going to react it with an ammonia-like compound, some kind of nitrogen compound. So this one is ethane amide, and I know it's an amide because I have that structure right there. So that automatically means amide. C double bond O N is the amide part. But since this thing is 2 carbons long, I say ethane and then amide. And then this one is propane amide because it's the same situation, but it has 3 carbons on it. And so what I did with the next one is I kept my propane amide, but then I also added a methyl group to the nitrogen. So then I have to say, on my nitrogen, I also have a methyl side chain. So I know these names look confusing and they're not, some of them are not super easy to say, but every portion of the name tells you something about the molecule's shape. So if I'm looking at this and I don't have a structure, I'm going to know there's a nitrogen present. I know that nitrogen is connected to a doubly bond O because it says amide. And now I look and I see this molecule has a total of 3 carbons in it. And then I also know that on my nitrogen, there's also a 1 carbon attached to it. And so then the rest of the molecule, I just fill in H's. So this nitrogen is missing a bond, and these carbons are that carbon's missing 2 bonds. This carbon is missing 3 bonds. And so that's how I come up with the structure based off of the name. I usually just work backwards. All right. We're going to get to Ethan's question about cis or trans now, and then another kind of situation that happens with organic molecules. All right, so there's an instance where something happens to the molecule that doesn't seem like, one, it's a big deal, and two, that it's hard to see at first. But the issue is it dramatically changes the molecule. And the odd thing about it is all the atoms are connected in exactly the same way, but they're still not the same molecule. Okay? So let's first, on the single bonds, there's 100% free rotation around all single bonds. They can just spin freely like a wheel on an axle. So if I'm looking, this is ethane right here, right? 2 carbons and just hydrogens attached to these 2 carbons. So if I'm looking at it from the side, I can just like hit that hydrogen right there and it would just spin around like a pinwheel. Because that's carbon-carbon single bond, it doesn't matter. It's just a straight line between the two and the thing can just spin. So when ethane gas runs into a wall inside of a tank, those hydrogens literally are going to spin around. But the moment that I've added a double bond, it becomes fixed because not only do I have the single bond between the carbons, I also have the double bond, which is above and below. And so what you end up with is something like this that can't flex. There's no flex to this anymore because I've got to be connected on the top and the bottom and in the middle all at the same time. So I can't flip that thing over because it has multiple connections. So these molecules are definitely different molecules. This is 1,2-difluoroethane and this is 1,1-difluoroethane. That's fine. They're not the same molecule because the fluorines are not connected to the same carbons. But let's apply that logic down here. So what's the name of that?
You're not screen sharing.
Darn it. So this molecule here, the 1,2-difluoroethane and the 1,1-difluoroethane, they're not the same molecule because the fluorines are not attached to the same carbons. Down here, though, what's the name for the first molecule here? This one. It's ethane. It's 2 carbons long. What is attached to my 2-carbon chain? It's 2 fluorines, right? So it's difluoro. Can you give me the numbers of the position of the fluorines? That's it. This is 1,2-difluoroethane. What about this one here? Sorry, ethene, not ethane. It's the same. And that's a problem. Because this molecule here and this molecule here, they have different melting points, different boiling points, different flash points, different chemical reactivity. They are different molecules, even though everybody's connected up the same. And so this is called a geometric isomer. And a geometric isomer is a geometric isomer because the atoms are connected differently in 3-dimensional space. It didn't matter on the single bonds because the bond spun, but now that the bond is the same, these guys are considered cis because they're on the same side of the molecule. And these guys are considered trans because they're on the opposite side of the molecule. And they're different molecules. So where have you heard those prefixes before? Cis and trans.
Cisgender and transgender.
Okay, anything else? Anything associated with nutrition? Trans fats, right? And cis fats. So what are your cell membranes made out of?
Protein?
No, what are you, a virus?
I haven't taken bio yet.
Well, I feel like everybody should know that after hearing months and months of coronavirus stuff. They're encased in proteins. That's why they're difficult to get access to. Your cells are not encased in proteins. They're encased in what? What are they surrounded by?
Fat.
Okay, a lipid bilayer. All
I
right,
would just say the mitochondria is the powerhouse of the cell.
that is true, but that doesn't have anything to do with what we're talking about.
Nothing else. Remember, nothing else.
It's a phospholipid bilayer.
It's a phospholipid bilayer.
My favorite kind of bilayer.
Doop, doop, doo. All right.
It's like it's hairy.
So this is the phospholipid bilayer. This portion that's blue is hydrophilic. The portion that's yellow is hydrophobic. The portion that's
it's like,
blue is hydrophilic. So the insides hate water, which is why they're attaching to each other. And the outsides love water, which is why they're on the outside. So the outside of the cell and the inside of the cell love water. So I
it's like
create
my semen.
I create this thing, and the fats that are inside of here, these are cis fats.
Oh, LDLs and HDLs, right?
Sure. So the cis fats themselves look like this kind of thing, where the double bond has the chain continuing on the same side, and the trans fats are on the other side. So the interesting thing about this, let's just put a cis and trans fat up there. This molecule right here with this curve in it, this is what your cell membranes are made out of. This one up here, your body has no use for this molecule. But it's a fat. So what does this molecule do?
Give you energy?
It could, but it doesn't. Your body doesn't want to use it for energy because it's difficult to metabolize because it's trans. So what does it end up doing with it?
Storing it?
Before that, before the conversion into a cis fat for storage, it floats around in the bloodstream.
Oh,
Do lipids want to float around in your bloodstream?
no.
So what do they do to stop floating around in your bloodstream? They'll latch on to anything that they can that they get close to. So if they run into the inside of your blood vessels and they have the ability to, they'll stick to it. And then what happens when the next trans fat sticks to it? And then the next trans fat sticks to it. Eventually, it clogs that vein or artery. So trans fats don't have a good biological use. And cis fats do. All of your cell membranes are created out of cis fats. Nature doesn't make trans fats. When you eat a pork chop, there are no trans fats in that fat. It's either no single bonds, no double bonds at all, and it's just straight like stearic acid or something like that, or there are cis bonds in it. So when you eat fat, say off of bacon, or let's use a peanut. So there's obviously a lot of oil in peanuts, and that oil is fat, and all of those fats are cis fats, not trans fats. So when you eat a peanut, if you look at the calorie content for a bag of peanuts, it says it's a large number. So the calories that could be used for energy are large. But when you eat that peanut, what do you think the fat from the peanut is actually being used for? Do you think you're actually using it for energy?
No.
You're not. What are you doing with it?
Well, we're
You're
not
making
having
cell
it.
membranes. You're building cells out of it. So if you look at like a Twinkie and a bag of peanuts and say, well, the Twinkie has less total calories in it, so the Twinkie's better for me. The answer to that is no, that's not better for you. I mean, it's an obvious answer, but what are some things that you could do with wood?
Burn it.
Okay, great. I can burn it and have some heat generated for me for a short period of time. What else could I do?
Build with it.
I could build with
Eat
it.
it.
So fat, what can your body do with fat, specifically cis fats,
Use it to build.
instead of using it for energy? So that number on the peanut bag talking about caloric content is completely misleading, because even though there are a lot of total possible calories there, your body's not going to use that to burn energy and not going to turn it into fat. Your body's going to make cell membranes because you're constantly making cells. Does that make sense? So that caloric content is incredibly misleading. Does anybody know how they get the caloric content for food?
Burn it.
Burn it. They burn it inside of a chamber that's sealed, vacuum sealed, and they check to see how much the water temperature's gone up. It's like that homework question I gave you where you put a hot piece of metal inside of in some water and the water heats up. That's what they do. They burn it and some water heats up. And so however much heat the water gain, that's how many calories are. Of course, if a peanut is using all of its protein and fat to turn it into energy, it's going to have more energy than a Twinkie does. But the stuff in a Twinkie isn't going to be used. So for building, so the big issue with this is carbohydrates are used for one thing and one thing only. Since we're not plants, the only thing we can use carbohydrates for is what?
Burn it in energy.
Burn it for energy. And if we don't need the energy, then what do we do with the carbohydrates?
Store it.
Store them as fat. If I eat fat, what are my body's options?
Energy or build something out of it.
Build it or burn it. You're going to build with it. When you eat fat, your body doesn't gain fat. It's not how it works. When you eat sugar, your body becomes fat. That's it. That's the end of the story. And this is about these, as far as it relates to these trans fats. Where'd that thing? Oh, I killed it. As far as it relates to the trans molecules, those molecules are not natural molecules. Does anybody know where we get trans fats from?
Wheat? No.
Like a lab.
Don't we hydrogenate existing fats?
So we hydrogenate an existing fat. So a hydrogenated fat, so it's a fatty acid, so there's the acid part. And to this, 1, 2, 3, 4, 5, 6, 7, 8. So these lines coming off are hydrogens. This is stearic acid. And so this would be the fat that you get off of bacon. This is a straight chain. Your body's going to use this for energy, most likely. You can use this for building stuff. You have a mechanism to convert this because it's not a trans fat. Okay, so if I take away that and I add a double bond there, that makes this an unsaturated hydrocarbon, unsaturated fat. This doesn't taste very good. So I have two options when I want to make Twinkies, and I need to use a fat to make my Twinkies because I'm gonna take my cake and I'm gonna add fats to it, and then make my cream filling out of fats. I don't want to have to kill cows and pigs because they're expensive. I'd rather squish corn and get fats out. So then how do I make my corn fat taste like animal fat? We do what Sheen said, which is hydrogenate. And to do that, I take this and I put it in a huge vat. I put some nickel metal in here, and then I add hydrogen gas. And then the hydrogens go up, and then they attach themselves here, and the double bond disappears. The problem is sometimes this doesn't happen, and the nickel actually causes this double bond here to turn into, instead of adding the hydrogens to it, it mutates the double bond. So this double bond is cis. Are we okay with that? Because the hydrogens are on the same side of the double bond. But if I flip it, and put the H on the other side of the double bond, this is trans. This is what margarine was for decades, like 80 plus years. So what would people tell you is a way to make sure you don't have a heart attack? Stop eating butter and eat margarine. What was margarine doing to people?
Giving them heart attacks
Giving
by
them heart
clotting their
attacks.
blood.
By clotting their blood because there are trans fats here. And the funny thing is, not so funny thing that somebody should have noticed a long time ago, is if I'm looking at the rate of cardiovascular disease in the United States, it looks like this. And if I look at the butter consumption, it looks like this. Sorry, the margarine consumption. It looks like that. I'm not sure why nobody noticed this, but it took a long time. So if you take a nutrition class from an old person, they'll tell you to eat margarine instead of butter. Why? Because they were taught that 40 years ago. So younger nutritionists are learning better stuff.
So I wanted to ask, earlier in the notes, it talks about cis-2 butane.
Yep.
What's it? Can you draw out what the difference would be between cis-2 butane and trans-2 butane?
Sure. Name this one this molecule right here for me. We've already got 1,2-difluoryl ethene from Ronaldo. So what's the prefix I put on this?
Cis.
That's it. What's the prefix I put on this one?
Trans.
Okay, so now let's go back up to that. So here's my cis-2 butene, right? So what's the cis-2 butene look like? I've got a carbon and a carbon and a carbon and a carbon. I have a double bond between carbon number 1 and 2, and I've got hydrogen, 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 hydrogen. And where do I put my other hydrogens? They're on the same side.
Okay,
So
I get it now.
That's a cis version. And if I put them over here, that would be the trans version. So that's a geometric isomer. These are geometric isomers. So you can see trans-2 pentene. Hey, what are you doing with those wire clippers? Give those back to mom right now. Now. Hey. Yeah, I'm gonna need a minute.
I was in a video, it's like, what do you have there? A knife! No!
Yeah. She's probably fine.
It's Rob's daughter, who knows what she's like doing out there.
She's probably fixing the car.
Or doing some chemistry or something.
Do these names make sense? So if you have a double bond, then you probably have a cis molecule or a trans molecule. So the first one, you see the hydrogens are opposite from each other, so it's trans. And the second one, you see the hydrogens are cis on the same side, so it's cis. The next one, it doesn't have to just be hydrogen. So the next one, what you're seeing is the chain, the main chain of this molecule does this. That's the longest chain. So what's the chain relative to each other? It's trans to each other. And what is it this time? It's cis to itself. So that's where those names came from. Okay, so now we're going to move on to the scariest thing with organic chemistry. So the scariest thing with organic chemistry is something that looks totally innocuous, but in actuality, it can be incredibly dangerous. So are we okay with the idea of mirror images? So hold up your hands. Are they the same thing? No. Your left foot does not fit in your right shoe. They're not the same. They're mirror images of each other. They're not the same thing. And that same thing can happen in organic chemistry. So the two structures I have here, the black one is a carbon, the green one is a chlorine, the yellow one is a sulfur, the red one is an oxygen, and the blue one's a nitrogen. but because of their orientation, they're mirror images of each other, meaning I cannot superimpose those two molecules on top of each other. So they're actually different molecules. So this is called a stereocenter. Those two molecules are stereoisomers of each other. The carbons themselves and the molecules themselves are referred to as chiral. So anytime I've got a carbon and the carbon is connected to 4 different things, I have a chiral carbon or a chiral molecule or a stereocenter. And the reason that that's a problem is if you take your key, your house key, and you put it into your lock, you can open up your door. But what if you flip the key over? It doesn't open the door. So what if instead the grooves that you had on your key, I flopped them to the other side? So I made a mirror image key. Would it work? No. And so since these molecules are basically keys to fit inside of stuff, if the key is a mirror image, then it doesn't fit. And if it doesn't fit, it either doesn't do its job or it does a job it's not supposed to do. Which one of these 3 molecules that I have up here has a stereocenter in it? Only the first one. The second one has hydrogens attached. And then the third one has methyl groups attached. So you have to have 4 separate things attached to the carbon for it to be a chiral carbon. Okay with that? So these things are called enantiomers of each other. That's a funny word to say, mirror image. Depending on which one you're looking at, it's either called an L or a D or a plus or a minus or an S or an R. Sorry about that. It's not important for us to know that other than the fact that these designations exist. So what we're saying is, depending on how you name this thing, if this one is the S version, then this is the R version. Or if this is the L version, then this is the R version. If this is the plus version, then this is the minus version. Okay? And, say again?
Like, how do you tell which is L and which is R if you're not told either one?
We're not going to talk about it because we don't need to. And why did this thing all of a sudden just disappear off to the side of the screen? What it has to do with is designating the central carbon as your chiral center, and then picking whichever thing it's attached to is most reactive, and then going around in a circle. So in this molecule right here, the
Wait, you're not screen sharing.
thanks.
Also, can you tell me what chiral means again?
It means a carbon attached to 4 different things.
Okay.
And each of those things has to be different things. So this remnants of a carboxylic acid is the most reactive substance. And then this group right here, this basically amine group, is the second most reactive substance. So I would start at the carbon and go out to here, and then I would go this direction, and then this direction, and then this direction. So this is an L, or a minus, or an S, because it goes in a counterclockwise orientation based off of chemical reactivity. Again, doesn't matter. Just know that we've got multiple versions. So why is this important? Have any of you heard of this thing here? It's pronounced thalidomide.
Didn't it like kill a bunch of babies?
It
Or, like
it-
mess them up?
it messed a bunch of babies up. It didn't, I don't actually, it probably did kill some of them, but really what it did is this drug was developed as a anti-morning sickness drug. So I mean, most women have some sort of morning sickness at least when they first get pregnant, and sometimes through the entire pregnancy. Like you look at a pickle and you barf, right? That kind of situation. And some people, it doesn't last for very long, and some people, it's no big deal. But with some women, the morning sickness is so bad that they can't eat. So you need to be able to settle a person's stomach so they can actually consume calories so they can feed the baby and they can both live. So thalidomide was used in this, and it worked great. It actually quelled morning sickness. Problem. In a decent portion of the women who took this drug, their babies came out very deformed. And by very deformed, I mean like we're missing hands, missing arms, missing legs, missing a portion of their torso. Like there's not 9 ribs are missing. So very bad development issues occurred. This drug was never sold in the United States because it hadn't finished going through the FDA policy, which is great and terrible. The great reason is obviously nobody in the United States had this problem. The terrible reason is every time somebody wants to develop a new drug, they have to go through this long drawn out FDA process. And that process is so long that the people that this drug might save might have already died. So there are times when the FDA has been sued to get drugs through the FDA process faster, to get it to people who could use the drug, even if the drug kills them, because these people are already dying. Does anybody know where this happened most famously? AIDS medication. AZT, I mean, usually it takes 10 years for a drug to be able to be sold and prescribed. So AZT was a drug that stopped AIDS from killing people. So you'd have HIV, but you wouldn't have full-blown AIDS if you were taking AZT. The most famous person that did this was Magic Johnson. I mean, I don't know if he's famous for you because you guys are all young, but he's probably top 3 basketball players of all time.
I
And
think Magic Johnson is.
somebody in this room not know who Magic Johnson is?
I do not know who Magic Johnson is.
There you go.
Monica Shane.
He's a super famous basketball player, one of the greatest basketball players of all time. Some people would consider him the best basketball player of all time. And he contracted HIV and he never got AIDS because he's a multimillionaire. And so when the drug company produced AZT, he said, I want it, sell it to me. I'll stand in Canada and you can hand it to me. And that's what happened. So he got the supply of AZT before everybody else did because he could afford to do it, which, you know, is usually what happens with rich people. But then the people who weren't rich took this to the Supreme Court and forced the FDA to allow AZT to be thrown through on an emergency route. And because of that, we have a different route like we have right now. So usually when a vaccine comes out, it takes 10 years for it to be able to be used by people. Are we going to wait 10 years if somebody develops a functional coronavirus vaccine? Of course not. We're going to be getting injected with it 3 months after it gets produced. So let's look at this molecule, this thalidomide molecule that caused all the problem. The molecules themselves are identical except for this carbon right here. So what's attached to this carbon that's designated as S? This is a carbon, but this carbon is doubly bonded to an oxygen. This carbon right here has 2 hydrogens on it. This is a nitrogen, and this carbon right here has a hydrogen here and then this large structure. So that's 4 different things attached to it. The reason I have to check the entire molecule is because you can't just say, okay, so this carbon right here is attached to a carbon and a carbon and a carbon and a hydrogen. Okay, great. So it's attached to 3 carbons, so it's not chiral. You can't just stop at the first thing it's attached to. You have to make sure that the thing that's attached to isn't the same as other stuff. So over here, I've got the exact mirror image. So one of these things caused birth defects, the S did, and the R version did not. So a person could take the R version of this and stop morning sickness, but what's the problem with that? When this drug is made, both the S and the R versions are created. It's called the racemic mixture. It's a mixture of the 2 stereocenters. So what do you think the resulting problem is?
How do you sort them out?
How the hell do I get these 2 things apart from each other? And the answer sometimes is you just can't. Why? because the molecules are identical with the exception of the stereocenter. So although this thalidomide is still sold, is still prescribed, it's only prescribed to men, and it's prescribed, I think, as a antidepressant, actually. I'm almost positive it's an antidepressant. But women are not allowed to get this because you could be pregnant. I mean, I read a story about like a 65-year-old woman who wanted a prescription of thalidomide because her husband had it and they wouldn't give it to her. She's like, I'm 65. I went through menopause 15 years ago. Give me the damn drug. I cannot become pregnant. So because the segregation of the molecules is sometimes impossible, what do you think the very first rule of I'm making a drug is for a drug company? Maybe rule number 2. Rule number 1 is it has to be able to solve the problem. Rule number 2 is it can't have a stereocenter in it. Because even if we make it, we're going to spend billions of dollars trying to separate that thing out. And if it does have a stereocenter in it and you can figure out how to separate it out, guess what the FDA makes you do? Run 2 totally separate trials. And I don't know if you know this, but those trials cost hundreds of millions of dollars. So now I do 2 of them, one with the R version and one with the S version, and I see what happens. And the best thing that can happen with the version that's not biologically active is it does nothing. The worst thing that can happen is that thing kills people. And then the end of this is just some reactions. So you know the first one, it's just combustion. The second one is incomplete combustion, and this happens if the oxygen isn't in plentiful quantity. So if you're looking at like a weed whacker, a 2-stroke weed whacker, they usually can't get enough oxygen, so the exhaust is black, especially when it first starts. Or an old car, the exhaust can be black, and you also end up with carbon monoxide being generated. I can halogenate something, meaning I can take a halogen and I attach it to something. So if I've got UV light, I can break apart the Br2, and when the Brs are separated from each other and by themselves, they kind of freak out, and then they bump hydrogens off of alkanes, and then you make an alkyl halide. You can actually take hydrogens off and make a double bond. If you have the correct temperature and pressure and some platinum, you can end up making hydrogen gas out of this. This process is not efficient, but it's definitely possible. We can make alkenes, make double bonds with alcohol. This is the most important reaction that we have for organic chemistry, for like on an industrial scale. This is phenomenally important because this molecule right here is the precursor. This can be the Lego for any structure you want to make. Any molecule that you as a chemist want to make, you can make it with starting with alkenes, with double bonds, because they're so reactive. So why is this the most important reaction? Tell me about this stuff.
Ethanol.
I can take corn, ferment it, and make ethanol. So it's a phenomenally cheap initial ingredient that allows me to get to a very useful ingredient or a very useful reactant. So they just finished one of these in Texas. It was BASF. I don't know if you guys know them, but they're the largest chemical manufacturer on the planet. It's a German company. If you own something, BASF probably made something that went in it. That's pretty much it. Unless we're talking about a tomato you grew at your house, it's got BASF stuff in it. They just finished a plant in, I think it was Killeen, Texas, that they'll be able to make over 100,000 metric tons of alkenes per year based off of alcohol from Iowa corn. So why are they doing this? Because we're going to run out of fossil fuels. And this is how we get to make all the things that we want. So what would happen if we ran out of fossil fuels besides the fact that gasoline would become non-existent? What's the other side effect?
Well, kind of need stuff for plastics. We have a big dependence on plastics.
Plastic is gone unless we do stuff like this. So the smart forward-thinking companies are trying to figure out ways to make plastics out of alcohol that you grow from corn because it's renewable. So anybody have any idea why that is a problem into itself?
Because the resources required to grow corn.
Instead of eating the corn, we make stuff out of the corn. So that automatically reduces the total food produced in the world, which is a problem, right? We already have people experiencing famine, so we don't want to take the food and turn it into something else because we like plastic. But that's where we are right now. The other reactions we've got are if I've got any kind of double bond, I could put hydrogen on it or water molecules or halogens or the binary acids, and I could make stuff. So this is why the double bonds are so important. I could do something dumb like take the double bond and get rid of it. Or I could take the double bond and I could put some bromines on it or halogens. Or I could take the double bond and add water to this and get an alcohol, which is also kind of dumb since I probably started with an alcohol. Or I could take an acid like this and attach it across the double bond, and now I've just got one halogen on it instead of two halogens on it. So the double bonds themselves are phenomenally useful because I can make lots of stuff. And the coolest part about it, and I didn't show it here, is I can start connecting the double bonded molecules to each other. So we have that styrene to make polystyrene because there's a double bond there. And so you end up having this repeated over and over again, and so you get styrofoam in the same way that I can repeat glucose over and over again to make starch or to make tree bark. And that's all I got. So we went through all the naming, but I'm not going to be asking you naming molecules. So the stuff that you're going to see is going to be, can you name this functional group? What is on this molecule? What kind of functional group is on this molecule? But if you take OChem, this would be the first day of class. This set of notes would be class day 1.
God. Are we gonna have anything besides nuclear and organic chem in the test?
Nope.
Sick.
Is it going to be 20 questions like the last few exams?
Probably. I haven't finished it yet.
Okay. Oh, hey, Professor Kovacic.
Yeah.
Did you get my message on Moodle?
Yeah, I responded to you.
Oh, you did?
I did.
I feel really stupid.
Not a big deal.
Wait, you wrote it to me? I didn't get a response.
Check your email.
Okay.
That's a weird thing. When you message me via Moodle, it shows in my inbox. And then I usually just respond to that. So it doesn't show up in Moodle, it shows up in your inbox.
Now, whenever you send messages over Moodle, I always get them in my email first.
Yeah. Well, we're hoping that the thing that you use to register is called RogueNet, and it's sort of a dead program. And we've been trying to get rid of it for a few years now. And we're hoping that by August, we will be on the new program called Campus Nexus. And when that happens, you'll be able to just log into your college email regular. You won't have to use the portal. Like, you can just have the Gmail app on your phone and it'll just populate. It does for the instructors. It just won't work for the students because IT people are rigid. Is really the answer.
Makes sense.
Anybody? Anything else?
Is homework 19 just going to be more naming?
I'm probably not going to give you a homework 19.
Sick! Awesome!
But there's points for a 19th homework in the grade book.
Well, we can just remove it then.
Yeah, it's gonna. Oops.
So do you just have it like all
I
scheduled
already
to release on
deleted it.
specific?
No. I'm sorry, say that again.
Do you just have it like all scheduled to release on specific days, or do you release them one by one?
I release them after class.
Okay.
That way I write the homework right then and I know how far we got, so you don't get a homework from some other year where we got farther and you're like,
Yeah,
what's
makes
this
sense.
homework question for? Alrighty. I'll see you guys on Thursday. Email me if you have any questions.
Thank you, Professor.
Turn in your labs. I'm still missing like 22% of labs.
Oh my god.
Will do.
Some of you, like, a lot of labs are missing.
Rob, I emailed